Let us solve question number 21. A 4-pole DC wave-wound generator runs at the 600 rpm. Flux per pole is 0.015 webers and generated no load voltage is 240 volts. Number of the conductors are option 1 600 and option 2 800, option 3 1000 and option 4 1200. So given that in this question, so option first one number of the poles, the P is equal to 4 number of the poles, and also mention that wave connected armature winding. So that number of the parallel paths in the wave winding is equal to 2 number of the parallel paths, and the speed of the generator, the N is equal to the 600 rpm. So this is the 600, the revolutions per minute, and the flux per pole pi is equal to 0.015 webers. Generated voltage under no load, okay, Easy is equal to the 240 volts, and we required number of the conductors. Okay, this number of the conductors is denoted by Z. So this is the generated voltage. So the number of the conductors are required. So we know how do we find out the generated voltage. The Easy is equal to phi Zn by the 60, pi Zn by 60 into the P by A. So now just substitute the given values in this equation. The generated voltage is equal to 240, the flux is equal to 0.015, the number of the conductors we need to find, and N is equal to 600 rpm divided by 60, and number of the poles, okay, this poles is equal to 4 number of the poles, so divided by the 2. So now just simplify this. This one is a 60 and it is a 10 times of the 60, and 2 into, okay, multiplied by 2, and next one, so this is a simplify here. So this Z is equal to the 240 divided by the 0.015, the multiplied by 10, okay, into 2. So by solving this we will get the 800, okay, number of the conductors. So number of the conductors in the armature core of the DC generator is 800 conductors. So that option 2 is correct for this question. And next one, question number 22. A wave wound DC generator with a 4-pole 1000 conductors having flux per pole of 0.06 webers is developing a voltage of 200 volts. So then the speed of the armature will be, so option 1 200 rpm, option 2 100 rpm, and option 3 400 rpm, and option 4 600 rpm. So in this question, number of the poles, okay, given in the question. So number of the poles P is equal to 4 number of the poles, and also mentioned that wave connected armature winding. So that number of parallel paths A is equal to the 2 only, and speed number of the conductors, 1000 conductors are there, the Z is equal to 1000 conductors, and flux per pole, the phi is equal to 0.06 webers, and generated voltage of the generator, the Easy is equal to the 200 volts, and we required the speed of the armature in rpm. So N is a required, okay, this one is that. So how do we find out generated voltage in the generator? So we know the formula Easy is equal to phi Zn by the 60, the into P by, okay, A. So this just substitute these given values in this equation. Generated voltage is equal to 200, the flux is equal to 0.06, number of conductors are 1000, and we need to find out the speed N divided by 60 and multiplied by the number of the poles is equal to. So now here poles is a 4 number of the poles, okay, multiplied number of parallel paths is equal to the 2. So just substitute. So this one is the 60 will be cancelled, 0 will cancel, and also this is the 6 and the 6, okay, this will be the cancelled out. Now it is equal to the 2, so that so n is equal to the 200 divided by 2. So this is the 2 times, okay, 200, so it is a 100 times, so that and the 100 RPM. So option the 2 is correct for this question. And next one, question number 23. A lab-wound DC machine has 400 conductors and 8 poles. The voltage induced per conductor is a 2 volts. The machine generated voltage of 100 volts, 200 volts and 400 volts. Option 4 is a 800 volts. So given in the question, the number of the parallel, this is the number of the poles in the machine. So P is equal to 8 number of the poles, and number of the parallel paths. Mention that wave connected armature, lap connected armature winding. So that number of the parallel paths in the lap is equal to the P. So that is equal to 8 number of the parallel paths. And also mention that the generated voltage per conductors or voltage, okay, per conductor. So it is equal to the 2 volts. So we require the generated voltage, okay, per path. Okay, this is the generated voltage. The machine generated voltage means always generated voltage is represented with represented per parallel path only. So that's why we need to find out the generated voltage. So now generated voltage, okay, this generated the voltage, okay, per path. So this is equal to the generated voltage, okay, per conductors, so multiplied by the number of the conductor per parallel paths. Okay, also mention that the 400 number of the conductors, okay, this number of conductors is equal to 400. So this formula is required to answer this question. The generated voltage per path, so this is represented with this is a EZ. The EZ is equal to generated voltage per conductor multiplied by number of conductors per parallel paths. So therefore the EZ is equal to, so what is the generated voltage per conductor which was given in the question? So that is equal to 2 volts, and number of conductors is equal to 400 conductors. How many number of the parallel paths? 8 number of the parallel paths. So now this value, by solving this we will get, so 4 times, okay, that is equal to 100 volts. So that answer for this question, option 1 is correct, 100 volts. And next one, question number 24. The armature of the DC machine is laminated to reduce the option 1 hysteresis loss, eddy current loss, the mass and the inductance. Armature core of the DC machine is laminated to reduce eddy current losses. By laminating the core, the conductivity of the material decreases. The decrease in the conductivity decreases the eddy current losses. So that option the 2 is correct for this question. Always eddy current loss directly proportional to the conductivity of the core. So by laminating the core material, conductivity of the material is a decreases, and decrease in the conductivity, eddy current losses will be decreased. So option 2 is correct for this question. And question number 25, the direction of rotation of the DC motor can be determined by option Fleming's right hand rule, the Fleming's left hand rule and Lenz's law, Ampere's, okay, this is direction of the rotation of the DC motor. So now we are force direction, force developed by the current. So now it can be obtained by using the Fleming's left hand rule. So according to Fleming's left hand rule, suppose assume this is the forefinger and center finger, okay, this one is the center finger and this is a thumb of the left hand, okay, this thumb of the left hand, okay, this is thumb of left hand. So if forefinger indicates, okay, this one is the forefinger, that indicates the direction of the flux, center finger indicates the current direction. So then thumb indicates the rotation of the conductors, okay, rotation of conductors or force developed by the conductors, okay, it is not force applied, the force developed by, okay, conductors, got it fine. So now this is unknown parameters, okay, it is unknown. So if we know these two, we can find out the direction of the rotation of conductors or force developed by the conductor. So which law we can use to find the direction of the rotation of the motor? So that is the Fleming's left hand rule. So that answer for this question, option the 2 is correct. Okay. And next one, question number 26. The armature resistance of the 6-pole lab-wound DC machine is 0.05 ohms. If the armature is rewound using a wave winding, so then the armature resistance will be option 1 the 0.15 ohms, and option 2 0.1 ohms, and option 3 0.3 ohms, and option 4 0.45 ohms. So here mentioned that 6-pole lap wound and it is a rewound as a wave winding. So then what is the armature resistance here? So armature copper losses, suppose I square R loss in case of the lap winding always is equal to I square R loss, so in case of the wave connected armature winding. So if the same machine is reconnected as a wave from the lap winding, there is no change in the copper losses remain same. So now from, let assume, this is assume as a equation number 1. So we know the always current rating of the machine, current rating is directly proportional to the number of the parallel paths. So now this is the equation number 2 here. So from 1 and 2 equations, okay, this 1 and 2 the equations, okay, we get, so this is a from 1 and 2 equation. So number of the parallel paths in the lap winding, this is the square, I square is number of parallel paths square multiplied by the armature resistance in the lap connected armature winding, and number of the parallel paths in the wave connected armature winding, the multiplied by the resistance in case of the wave connected armature winding. So now by using these 1 and 2 equation we can get, so number of the parallel path relation and also the resistance relation. Now just substitute number of parallel paths in the wave connected lap connected armature winding. So that number of parallel paths, okay, is equal to, okay, number of the poles. So therefore 6 square and the resistance when the winding is a lap, okay, is equal to 0.05. The number of parallel paths in the wave winding always is equal to the 2. So 2 square multiplied by the resistance in the wave connected armature winding. So now this one is the resistance, okay, in the wave winding. So now here the substitute. So our resistance in the wave winding is equal to 36 multiplied by 0.05 the divided by 4. So resistance in the wave winding. So now this value is equal to 0.45 ohms. So like this we can answer this question, and this question can be answered by using another way also. So let us start another way one. So initially yes. So initially winding is connected in the lap, okay, lap winding nature. So lap winding point out. So lap winding number of poles is given 6 number of the poles in case of the lap. So how many number of the parallel paths? A is equal to the P, so that is equal to 6 number of the parallel paths. So now let us draw the 6 number of the parallel paths. So this is the resistance per one path. Now similarly resistance per path. Okay, this is also resistance per path, all the resistances, the 6 number of the parallel path, okay, this is a, okay, 6 number of, so these are positive group of the brushes, okay, assume as positive group of the brushes, and these are the negative group of the brushes, this one is the negative group and it is a positive group of the brushes. Now this total resistance, okay, it is known as R equivalent, okay, this R equivalent. So that is equal to resistance of armature winding, so in the lap winding, so which was given 0.05, okay, this one is the 0.05. So by using this, okay, resistance per path, so how do we get same resistance here? So therefore R equivalent is equal to the resistance per path in the lap winding, the divided by 6. So therefore the resistance per path, so this per path in case of the lap, okay, in the lap winding. So it is equal to, so now here this is the 6 multiplied by R equivalent, the 6 into okay 0.05. So now this one is the 6 into 0.05. So it is equal to 0.3 ohms. Okay, 0.3 ohms. This is the resistance per pass in the lap connected armature wind. Now if the same machine okay is reconnected as a wave, okay, then what will happen? So if the same machine is reconnected as the wave winding, okay, then what will happen? How many number of the parallel pass in the wave winding? A is equal to 2 number of the parallel pass. So that means 3 parallel pass conductors, a 3 parallel pass will become a 3 parallel pass are connected in series and act as a 1 parallel pass in the wave connected armature wind. So like this, suppose resistance 1, the resistance okay, 3 parallel pass are connected in series. Now similarly 3 parallel pass okay, are connected in series. So like this is the negative group of the brushes and it is a positive group of the brush, negative 1. Now we require okay, this the R armature resistance of the wave wind, okay, R equivalent armature resistance in the wave winding. So that is nothing but R equivalent is required in the wave winding. So now what is the resistance per path? Okay, this value is equal to the 0. Okay, this one is a the 0.45. Okay, here the 0.3 and 0.3. So this is the 0.3. Now here also is 0.3 ohms, 0.3 ohms and 0.3 ohm. Now this is the 0. Total the resistance okay, per path. So this is the per path in the wave winding. So in wave winding is equal to 0.3 plus 0.3 plus okay, 0.3, all are connected in series. So now this value is equal to 0.9. So this is the resistance per path in the wave, but we required R equivalent in the wave connected armature winding. So that the armature resistance okay, in the wave winding, so that means R equivalent, the same value of resistances are connected in the parallel. So therefore the resistance per path, so divided by okay, 2. So 0.9 divided by 2 is equal to 0.45 ohms. So like this also we can answer this question. So we have two methods to answer this question. So by using the concept of parallel pass we can answer this one, and other way also we can answer, suppose by using the circuit theory, so we can answer the question. So this was very important question for competitive exams point of view. Now next let us solve question number 27. The number of the parallel pass in the armature winding of a 4-pole wave wound DC machine having the 22 coil sides is. So number of parallel pass are this always in wave winding. So in the wave winding, so what will happen? Number of the parallel pass always is equal to the 2 number of the parallel pass. So that option the 2, okay, option 1 is correct for this question. And next one, question number 28. So if the number of the conductors and the speed of lap wound DC generator is double, then the generated voltage, okay, generated EMF, that will be option 1 remain same, double the former value, 8 times of the former value, 4 times of the former value. So now if the number of the conductors, okay, let assume, so let assume here, so this is a, let Z is the number of the conductors, and the N is a speed of the generators, and the mention in the question, the given that, so number of conductors are double, that means the Z number of conductors in the case 2 is equal to the 2 times of the number of conductors in the case 1, and also the speed in the case 2 is equal to 2 times of the speed in the case 1. So this is given, and also this is the, we required the generated voltage of the generator. How do we find out generated voltage? So what is the relation? We know the generated voltage is equal to the phi Zn by 60 the into P by A. So this is the generated voltage in the generator. So from this equation, flux here, the flux, number of poles and number of parallel paths are fixed, but only generated voltage and number of conductors and speed are double. So from above equation, okay, equation, So we get this one, the generated voltage directly proportional to product of the number of conductors and the speed of the generator. So this equation can be written as the Eg2 divided by the Eg1 is equal to Z2 divided by Z1, the into N2 divided by N11. So Eg2 is equal, so we require the relation the Eg2 and the Eg1. So this is equal to N2 is equal to 2 times of the Z1. So 2 times of the Z1 divided by Z1, and speed is also 2 times of the N1 divided by N1. So now in this equation, see here, and this is the Z1 will be cancelled out, N1 is also cancelled out. The remaining terms, okay, Eg2 is equal to 2 into 2, so 4 times of the Eg1. So answer for this question, the 4 times of the previous value, so that option the 4 is correct for this question.